Hi, Chris Good here, and this is a solution to the repeated measures ANOVA problem, to the practice repeated measures ANOVA problems. Here, a therapist is interested in helping people with ophidiophobia, which I guess is fear of snakes. So they're going to slowly desensitize the patients to snakes. So we're getting a sample of 8 ophidiophobics with snake-related stimuli, presenting them with snake-related stimuli, measure their physiological response, whatever that is. So these are measures of some physiological response, and presumably a higher number indicates more anxiety. Um, so I've copied these into an Excel spreadsheet, and we're going to do a similar solution that we did in practice problem 1, where we're going to fill in the source table as we go along, and we're going to present our findings that way. We're going to do all of the same things that we did in practice problem 1, right? All of these steps for null hypothesis significance testing. Let's do that now. The null hypothesis here is that the mu for group 1 is equal to the mu for group 2, which is equal to the mu for group 3. And an alpha point of 5, we need to find an F crit, and in order to do that, we need to fill in these degrees of freedom. So we're going to need the number of means that we're doing. I haven't calculated those yet. Let's go ahead and do that now, so we know what means that we're talking about here. Copy and paste are your friends. We'll need a count of all the scores. Right, there are just 3 groups in this one. Participant number isn't a variable, right? We'll need the sum of all the scores eventually. I think we can do degrees of freedom now. Oh, you know what? We'll need n's for each one of these groups. So we know that there's 8 people, right? 8 scores. All right, so now we can do, for each one of these groups, we can do between treatments. Oops, I forgot about the error. We can do degrees of freedom between treatments, which is k minus 1. We can do degrees of freedom within treatments, which is big N minus k. And we can do total degrees of freedom a couple different ways. We know that it's big N minus 1. But did you also know that total anything is equal to within plus between? That's how we're actually going to get within treatments. We're going to calculate the total sums of squares and between treatments sums of squares, and then we'll get within treatments sums of squares by subtraction, just like we did in the previous example. But now we're still on step 2. F crit is going to be evaluated at 2 and not 21, but at error degrees of freedom. So we need between subjects, so we can subtract from within to get error. Between subjects is the number of subjects you have minus 1. I only used one of those n's because it's just the count of the participants here, 8 participants. So now we can get error degrees of freedom by subtraction. Within treatments minus between subjects equals error. That's the same for degrees of freedom, and it's going to be the same for sums of squares. So this F crit is going to be evaluated at 2 and 14 degrees of freedom. If we go to the F table, right, here we go. At 2 and 14 degrees of freedom, F crit is 3.74. So F crit at 2 and 14 is 3.74, and now we need to calculate F. Well, I'm going to do between treatment sums of squares first. We just need to get the t's, right, the total of everyone in this group. We'll square those values. Oops. I want to square them there. And we'll divide those squares by little n. So between treatment sums of squares is sum of the t squared over n divided by g squared over big N. So we'll need g squared, that's g squared, and we'll need to divide that by n. Now we can get between treatment sums of squares. that's equal to the sum over t squared over little n minus g squared over big N. Oops. Parentheses minus g squared over big N. There we go. Now we can get our mean square. It's just sum of squares over degrees of freedom. And for within treatment sums of squares, we could subtract the mean from each one of those scores, square them, and do the same thing for this one and this one. But I'm going to get total sums of squares this way. I'm going to take the deviation of each score from what we call the grand mean, which is the average of all of the scores. And now I can get deviations of every score from the grand mean. I want to make sure that that's the same grand mean for all of these deviations, and then I'm going to square those deviations. There we go. Total then is the sum of the squared deviations of every score from the mean of all the scores. All right, and we don't really do total mean square because we don't ever use that. But now that we've got between and total, we can get within by subtracting total minus between. And now we could get mean square within, but we're not going to use that either. We need to get between subjects sum of squares so that we can get error sum of squares by subtraction. And to get that, we're going to need the p's, which I have a column for. But I'm going to get another column for p squared, and then a third column for p squared over n. So this is going to be p squared. This is going to be p squared over, not over n, over k, because it's the number of 1, 2, 3 conditions that we have. So we'll sum over those 3 conditions for each participant, like this. And then we'll square those values. Right? Copy that. And then we'll divide each one of those values by k. But we need to make sure that it's the same k for every participant. All right, now we get what we need for between subjects. It's just the sum of p squared over k minus our friend g squared over big N. And now we can get error sum of squares by subtraction. Within treatments minus between subjects gives us sum of squares error. Now we can get mean square, sum of squares divided by degrees of freedom, and we can compute f as the mean square between treatments divided by mean squared mean squared error. That's our f. It is greater than this, so our decision should be to reject. Move these back over here. And we can conclude that participants, well, how about this? There's a significant effect of snake type on participants' possessive plural physiological response with f at 2 and 14 degrees of freedom equal to 20.04 and p less than 0.05. Now, you know that means we need to do Tukey's HSD, which means we'll need Q. Q then is going to be evaluated on 3 and 14 degrees of freedom, so 3.7. And then HSD is equal to Q times this quantity, the square root of our mean squared error divided by n. So the honestly significant difference is 3.22. So let's look at these difference. Is 12.125 3.22 away from 9.75? Let's check. I don't think it is. No? Sorry. Let's label these. Rubber versus plastic. Rubber versus picture. And plastic versus picture. Those are the three comparisons we want to make. So that's equal to rubber versus plastic. This is equal to rubber versus picture. And this is equal to plastic. Oops. Plastic versus picture. Okay. Only two of these are significant, so we can say that post hoc testing with two keys, HSD revealed, the participants' physiological response was significantly higher after viewing rubber or plastic snake than after viewing a picture of a snake. With HSD equal to 3.22 and P less than 0.05, period. All right, that's our sentence. That's all we need to say. And I'll see you next time.